Hey, let's do another example from section 3.4 here. We want to find all the zeros of this polynomial right here. Then we're going to completely factor it over the real numbers and completely factor it over the complex numbers. So to do this task, we're going to find all the real zeros, or do our best to find all the real zeros. And for this task, we want to find all complex zeros. Okay, so we start by finding the real zeros. What we need to do here is use what we had in the previous section. So we want the rational zeros theorem. So if a rational zero exists, it has to be of a certain form, right? It's got to be P over Q, where P comes from factors of the constant term. So plus or minus 1 or plus or minus 5. And our Q, our denominator for our rational zero, has to be a factor of our leading terms. So that's, or excuse me, coefficients. So that would be just plus or minus 1. So this is good. We're going to have a pretty short list. P over Q has to be P. What is going on? P over Q. Oh my goodness. Excuse me here. P over Q has to be either plus or minus 1 or plus or minus 5, right? So short list, and we can find these zeros, right? Now we could go and multiply these through, right? Find the function values, and it would be certainly easiest if it was going to be the 1, right? We could probably pretty quickly see if we put a positive 1 into all these x values, it's not going to cancel out anything really, right? It's all going to be positive, so that's not going to get us 0. So if we put a negative 1 in there, this term and this term are going to be negative, and the others are going to be positive. So we're going to have negative 7 plus 11, which is also not 0. So right away we can say that 1 and negative 1, those don't work. And if we really need to put them in there, do it. Okay, so well, that leaves us with just 5 and negative 5. Now, 5 cubed and negative 5 cubed, we're going to start getting pretty darn big numbers. And with these, it might be easier just to go straight to the synthetic division part, because we're going to have, our numbers aren't going to be as big, right? If I put a 5 here, I can see if this works, right? So we bring down a 1, right? And then we proceed, right? Multiply by 5, we add, multiply, we add, and pretty quickly we're going to get something that's not 0, right? Because I'm going to multiply 61 times 5, whatever that is, but either way I'm not going to get 0, right? So we know that it's not 5. So we can try the only one that remains, so hopefully this works, is negative 5. So bring down your 1, we multiply, we add, we multiply, we add, we multiply, we add, and we got a 0 remainder. So this tells us that x equal negative 5 is a 0, which tells us that x plus 5 is a factor, right? And we can take that and say, hey, my original polynomial, I forget if it was called, yep, it was called f, but we can write it as a product involving x plus 5 and the quotient that we found right here. So that would correspond to a quadratic polynomial. So we would have x squared plus x plus 1. Okay, so now what? Now that we have a quadratic, we can find the remaining zeros of this thing. So zeros are, well, it's just the quadratic formula, right? We're solving x squared plus x plus 1 equals 0, right? And we can use that quadratic formula. So we've got x is negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. And then reducing this, we got negative 1 plus or minus 1 minus 4 would be negative 3. So we got square root of negative 3 over 2. So that would be 1 plus or minus I times the square root of 3 over 2. Which, I mean, we can write this as in standard form for a complex number. Just like that, right? So our zeros now are this number right here and these numbers here. So we found 3 zeros, which we expected, right? Okay, so when it says to factor the polynomial over the real numbers, we've done that task right here, right? This is the factorization where each of the factors are either linear factors or they're irreducible quadratic factors. And that's what we would call this one, right? I cannot factor that without using those complex numbers or the strictly imaginary parts, right? So this is our real factorization. And then our factorization over the complex numbers, we would just go one step further and write the quadratic factor as a product of, well, those two zeros, right? So we got x minus the 1 0, so minus 1/2 plus square root 3 over 2i. And then I ran out of room here. X minus negative 1/2 minus square root 3 over 2i. All right, so that wasn't part of it. It's separate. So we might want to write this with our negatives distributed through, but that's kind of a formality, and we don't necessarily need to do that, but we can if we want to. So this one on the bottom, this is factored over the complex numbers. And the other one up here was factored over the real numbers. So great, there was another example here from section 3.4. Thanks for watching the video. Have a great rest of your day.